Hey everybody, and welcome to this video on solving systems of equations by substitution. So let's make it happen. Alright, consider this system of equations. Y equals negative 3x minus 1 and y equals 2x plus 9. Now, we could solve this system by graphing. But that took a lot of work. That was a bit tedious. And I'm wondering, is there any other way to solve this system of equations a little bit more efficiently? Now, even though we already know the solution, because we already solved this by graphing, let's pretend that we don't know the solution to this system of equations. So let's assume that there's some ordered pair solution, x comma y, such that both of these statements are made true at the same time. So we're going to assume that they're both true, and we're going to see if we can find out anything about x and y now. Well, if they're both true, that means that y is equal to negative 3x minus 1, and y is equal to 2x plus 9. Now this may seem a little repetitive, but y equals negative 3x minus 1. That means y is the same thing as negative 3x minus 1. Y and negative 3x minus 1 are the exact same thing, which means that anywhere we see a y, we can replace it with a negative 3x minus 1 because they're the same thing. Well, let's go ahead and let's replace the y in the second equation with negative 3x minus 1. And that's a totally okay maneuver because y is equal to negative 3x minus 1. Now, what was the entire point of doing that substitution? We did that because now we have an equation with just one variable in x. We can solve this equation, no problem. So what we just did is we said, if both of these statements are true at the same time, then this equation must be true. And if this equation is true, then it must be the case that x equals negative 2. So we just found the x-coordinate for the solution to this system of equations. Well, now that we have the x-coordinate, how are we going to find the y-coordinate? Well, we know that together, the x and y coordinates, when we substitute them in for x and y in either equation, will make the equation true. So we can substitute this x-coordinate of negative 2 into either of our original equations and find the y-coordinate. So we see that we have the solution to our system of equations. The solution to our system of equations is the ordered pair, negative 2 comma 5. And no matter what, whenever you solve a system of equations, it's best to tell the reader the solution in an ordered pair. So just to recap, we assume that both of these statements are true. And if both of them were true, we could substitute negative 3x minus 1 in for y, and therefore this equation is true. And if that equation is true, then x has to equal negative 2. And if x has to equal negative 2, then y has to equal 5. And therefore, if both of these statements are true, if there's a solution to this system of equations, then that solution must be negative 2 comma 5, which is exactly what we got when we graphed. All right, let's try another. Now let's try to solve the system of equations m equals negative 2k plus 6 and 3k plus 4m equals 4. Now a big difference here from our first example is that we don't have just m equals and m equals again. Remember before we had y equals negative 3x minus 1 and y equaled 2x plus 9, so we just got to set negative 3x minus 1 equal to 2x plus 9 and life was good. That's not the case here. Now if we want, we could totally solve this second equation for m. But just looking at it, I can tell that there are going to be some nasty fractions there, and I'm sure we can handle it, but I'm a little uneasy and that might be a little bit tedious. Could there possibly be an easier way? Well again, let's assume that there's an ordered pair, k comma m, that makes both statements true at the same time. That is, let's go ahead and assume that both of these statements are true. Therefore, m is equal to negative 2k plus 6. m and negative 2k plus 6 are the same thing. Therefore, wherever we see an m, we can replace that m with a negative 2k plus 6 because they're equal to one another. And when I look at this second equation, I see an m. So we can substitute negative 2k plus 6 in for that m. So what we said is, if these two statements are true at the same time, then this statement must also be true. Now, why would we do this? Again, we did so because now we have an equation with just one variable in it, and this will be no problem to solve. So, we find that if both of these statements are true at the same time, if there is a solution, then the k value of that solution must be 4. Now that we have the k value of our solution, all we need to do is substitute this into either of our original solutions to find the m value. No matter which one we choose, we should find the same m value. But we might as well substitute it into the first equation, as it looks like that one might be a little easier. And we have our solution. Remember, it's always a good idea to write our solution as an ordered pair. And if we're using variables that aren't x and y, it's a really good idea to write a generic ordered pair right above it using the variables so the reader knows exactly which number goes with which variable. Let's quickly check our solution to make sure it works. Awesome, so our solution checks out. Now, we very well could have solved both equations for m, and while it would have been a little bit harder and a little bit longer, it would have definitely worked. So as you can see, that took a whole lot of work, and that was just to find the k value of our solution. So yes, you can solve both of these for m, but since at least we had one of them solved for m, we were ready to substitute right away. Alright, here's another system of equations for us to solve. 3y minus 2x equals 12, and 2y plus x equals 1. Now in this case, neither of the equations are in variable equals form. In our first example, both of our equations were in y equals form. That made it so easy to substitute, and we were good to go. In our second example, only one of the equations was in m equals form, but that was totally fine. Even having just one, we were ready to substitute, and we were good to go. But now we've got neither of these in variable equals form. So first things first, I think we need to solve one of these equations for a variable. When I look at this first equation, it doesn't really appear like it's going to be easy to solve for either of those variables. There are going to be some funky fractions involved, and I don't really like working with fractions. Let's take a look at the second equation. We could solve for y, but I see already that there's going to be some fractions again. It actually appears that solving for x in the second equation will be easier because we have an x hanging out all by itself. A lot of times people gravitate towards solving for y, but you can solve for either variable to use the substitution method. So I'd say solve for whichever one looks like it's going to be the easiest and won't leave you with any fractions. So let's go ahead and solve for x. So now it's like we're solving the system of equations 3y minus 2x equals 12 and x equals 1 minus 2y. Again, let's assume that there exists some xy ordered pair so that both of those statements are true at the same time. So we're assuming that they're both true. That means that x equals 1 minus 2y. That x is the same thing as 1 minus 2y. That x and 1 minus 2y are the exact same things. That way, if there's ever an x anywhere, we can replace that x with a 1 minus 2y because they're equal to one another. Well, in our first equation, I see an x right here. And therefore, we can go ahead and replace that x with a 1 minus 2y. Let's do it. Once again, now we have an equation involving just one variable. Let's go ahead and solve for y. Alright, so just to recap, we assume that both of these statements are true at the same time. And if both of these statements are true, then both of these statements are true. And if these statements are true, then this equation is true. And if this equation is true, then that's the y-coordinate. So if this system of equations has a solution, then the y-coordinate has to be 2. And if we want to find the x-coordinate, all we have to do is substitute the y-coordinate in any of these equations, and we will find that x-coordinate. Pick the one that's easiest. I think x equals 1 minus 2y looks easiest. So we find the x-coordinate of our solution to be -3, and therefore the solution to that system of equations is negative 3 comma 2. All right, now it's probably time for us to discuss a general strategy for solving systems of equations using substitution. First, if you don't already have an equation in variable equals form, go ahead and turn either of the equations into an equation of the form variable equals some expression. And it doesn't matter which variable you solve for, choose the one that's easiest. Then, substitute that expression in for the variable in the other equation. This will create an equation with just one variable, which should be easy to solve. After solving that equation, substitute its solution into either of the original two variabled equations to find the other coordinate of the grand solution to the system of equations. All right, now for some practice problems. Why don't you pause the video and please solve each of these systems of equations using substitution. And note that in each of these, you have at least one equation in variable equals form, so they shouldn't be too tough. All right, two more practice problems, and these are a little tougher because none of these equations are in variable equals form. So you're going to have to figure out which variable to solve for in which equation so that you can go ahead and do some substitution. So why don't you pause the video, please solve these systems of equations, and then play the video to see how you did. All right, so I hope those went well for you. Now there's something I do want to point out. Now let's take a look at this second example for a moment. Of course, in the beginning, neither of our equations were in variable equals form. But then we went ahead and we solved that second equation for m, and we got m equals 1 plus 4a. Of course, then we substituted that into our other equation. Now what I want to know is what happens if we take the second equation, like we did, solve it for m, but then substitute that expression for m right back into the same equation that we used to get it. So that is, what if we ended up with this new equation? Of course, it's got only one variable. Shouldn't this help us find the solution to our system of equations? Well, note that if you try to solve for a in this equation, you get negative 2 equals negative 2. Of course negative 2 equals negative 2. That's an obviously true statement. But we only got that statement because we used the second equation to solve for m, but then substituted that right back into the same equation. And if you do that, you're going to get some sort of obviously true statement like negative 2 equals negative 2. And why I'm bringing this up is that in our next example, we're going to talk about what it means when you actually solve a system of equations correctly and get something like negative 2 equals negative 2. So if you ever get a statement like this, you want to make sure it's not because you made a mistake and substituted back into the same equation that you used to solve for a variable. All right, two last examples. Now I'll be honest with you, when we try to solve these by substitution, some funny stuff's going to start happening. But anyway, let's just start with the first system of equations. Please solve the system of equations y equals 2x minus 1 and 6x minus 3y equals negative 15 using substitution. So why don't you pause the video, take care of it, and when you're done, play the video and we'll reconvene. So when we tried solving this first system of equations, we ended up with the obviously false statement 3 equals negative 15. What does that mean? I mean, there's certainly no value of x and y that will ever make 3 equal to negative 15. Remember, when we did this substitution, we assumed that there was a solution. We assumed that both of these equations in the beginning were true at the same time. And what our work has shown is that if there was a solution, if both of these equations were true at the same time, then it also had to be true that 3 equals negative 15, which obviously isn't true. And therefore, we conclude that there are no solutions to this system of equations. This is one of those inconsistent systems that we talked about before. And in general, if we're ever solving a system of equations and obtain an obviously false statement, this means that the system of equations has no solutions. And note to self, if we had solved both of our original equations for y, we would have gotten y equals 5 plus 2x and y equals negative 1 plus 2x. Of course, y, whatever number that is, can't possibly be both 5 plus 2x and negative 1 plus 2x. And if we had tried to solve this system of equations graphically, these two are parallel lines. They have the same slope, but different y-intercepts, so they never intersect. One more reason we know this system of equations has no solutions. All right, now let's try the second system of equations. Why don't you pause the video, try to solve it, and when you're done, play the video, and we'll reconvene. So in the second example, when we solved by substitution, we got an obviously true statement, 10 equals 10. Now what does that mean for our system of equations? Whenever we're solving a system of equations and obtain an obviously true statement, like 10 equals 10, it means that the two equations we were working with originally are actually the same equation. Let's go ahead and solve that second one for n as well. And so we confirm that our original two equations in this system were actually the exact same equation in disguise. So therefore, if an ordered pair makes one of these equations true, it makes both of these equations true. And since each of these equations has infinitely many solutions, therefore this system of equations is going to have infinitely many solutions. This is a dependent system of equations, just like we discussed before. And in general, if we're ever solving a system of equations and obtain an obviously true statement, this means that the system of equations has infinitely many solutions. And again, even though there are infinitely many solutions, this doesn't mean that all real numbers are solutions. So we need to describe the solution set to the reader by just copying down one of the original equations from our system. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.